Before we start to implement binary genetic algorithm in MATLAB, we need an optimization problem. And let's define an optimization problem and solve the problem using genetic algorithm. We're going to minimize the value of f of x, and f of x is defined by this, the summation for I from 1 to n of xi, and we know that xi is either 0 or 1. These are binary decision variables, and that's for I equal to 1, 2, 3, up to n. And we know that the solution of this problem is xi star equal to 0. And this problem is known as min1 problem. This is a simple problem, but it's a good problem to start, and we will implement our binary genetic algorithm to solve this problem in MATLAB. Okay, let's go into MATLAB, and I'm going to define the min1 cost function here using the editor. Let's define a function, and the returning variable, the output variable, is defined and indicated by z, and let's name our function min1, and the function accepts a single parameter named x, and z will be equal to the sum of elements in x, and that's it. We define the min1 function in this file, and let's save it. After this, let's create another script, and this script will be our entry point to run the application. So let's clear this screen, let's clear the workspace, and let's close all of figures opened before. And I'm going to divide this script into several parts, and each part is doing a particular task. The first part, the first section, is problem definition. And in this part, we're going to define the problem, actually the cost function or objective function, and the search space. After this, we're going to set parameters of the algorithm, parameters of GA. So GA parameters is the second section of the script. And finally, we're going to run the algorithm and run GA to solve the problem defined here in first section. We're going to run the GA using these parameters, and we're going to have results. So we have a results section. So let's save this as app1. And we're ready to define problem, and we're ready to set GA parameters and then run GA using a function which accepts problem definition with parameters of GA and then returns back the results of optimization process. Okay, let's define the problem, and the main characteristic of the problem, I think, is the objective function. And here you want to minimize the value of min1, so it can be referred as a cost function. So I'm going to define cost function here, or simply you can name it cost func if you want. And the cost function is a handler. We use @sign to define function handlers in MATLAB. @sign min1, and that's, you can use cost function, the value of this function, but using this notation enables us to use cost function everywhere we want to refer to the cost function. And if for another application the min1 changes to another function, so you just need to rename this part, and the cost function remains same in all of our script and program. So let's roll back this change. A general notation similar to this is available too, which is a more generalistic definition of a function handle. And we have a function of x, a general, unnamed, untitled, anonymous function of x, which returns the value of min1 for that x. And for example, in some cases, there are some other parameters of our function, and we want to pass some predefined values as the second or third parameter. but we want cost function as a single input function. So we can use this general notation and it is extendable. So I'm going to use this notation instead of this, and I'm going to remove this line. The cost function is defined here. The next important part about the problem definition is the search space. The search space and the structure of solution is defined by how many decision variables we have and what type are they and what is the range of each variable, and these are defining decision variables or search space. Here we know that all of variables are binary, so the number of variables will be enough to define the search space. So I'm going to define n_var as number of variables equal to, for example, 10. We're going to solve for 10 binary variables. However, we're going to encapsulate these properties inside a structure, inside an entity named, for example, problem. So I'm going to define problem dot cost function. This creates a structure, a struct actually, and this adds a new field named cost function, and the value of this field will be this function handler. Similarly, we can define n_var field of problem structure. And if we run this program, let's save it and hit F5 or hit this. If we run this, then we will have problem, a one-by-one struct here. And if we check for the value of problem, we'll get this struct with fields, cost function with this value, and n_var with this value. And for example, if you want to get the number of variables in this problem, it's 10. And that's it. If we want to pass the information of problem into a function, then we just need to pass the structure problem, and that's enough. That will carry any information needed about the problem. And by these two lines of code, we have defined the function exactly, and we will use this information to solve the problem when we reach the third section. Next, we're going to define the parameters of genetic algorithm. In this section, we're going to define parameters of genetic algorithm. First of all, let's define the population size as npop. For example, we will use 20 population members, 20 individuals to create our initial population, and the population size will be constant for any generation. And let's define the maximum number of generation or maximum number of iterations we have. It can be defined as this parameter, maxit. I'm going to define this, maxit, and that's, for example, 100 iterations will be enough for now. We can tune this parameter as well. Okay, we have other parameters too, but we will add them whenever we reach the parts of the algorithm. For example, for crossover, we have parameters. For mutation, we have parameters. And maybe there are some other parameters too. We will define them when we reach and when we will want to implement. We will add the needed parameters here. But for now, I'm going to encapsulate these two parameters, which are common among all evolutionary algorithms and all metaheuristics. Always we have a maximum number of iterations and some population size. These are two common parameters of metaheuristics. But the other parameters differ from algorithm to algorithm. For now, I'm going to encapsulate these two parameters inside a structure named params, or I'm going to set params, and that's it. We defined another structure named params, which contains the parameters of the genetic algorithm. Now we're ready to call genetic algorithm, but we have not implemented GA yet. But the general calling scheme of genetic algorithm will be in this form. We have an output variable named out, and we have a function run GA, which accepts a parameter named problem. We're going to solve this problem, this optimization problem, using this set of parameters for the algorithm. So that's it. We're going to run GA using this problem data, and we're going to run GA to solve this problem using this set of parameters. But we don't have a function named runGA, so we're going to define this exactly with same signature. So we're going to create a function which returns a variable named out, and the function name is runGA, and accepts two parameters, problem and params, and then we will define the function in this way. Let's save this, runGA, and these warnings are because the parameters and arguments are not used, they are unused, and if we complete the definition of this function, the warnings will be resolved. Okay. From now, we're going to work inside this function, and this function will be called from our main script, and we know that problem has two fields named cost function and nvar, and params also has two fields for now, and we will add other parameters as well in future. But we're going to define the genetic algorithm, and we will implement GA inside this function. Okay, first of all, let's extract information from problem, the problem info, or simply problem. We have cost function defined as problem dot cost function, and let's add a semicolon here to suppress the output, and we have nvar equal to problem dot nvar. This enables us, using the structures, enables us to pass information in a structured way into functions, and the order does not matter here. And we can encapsulate any amount of data in any structure we want, and then we can extract information from the structure if we want. Okay, and let's extract parameters. Let's extract parameters. I'm going to extract the params. Max it will be params dot max it, and npop will be params dot npop. That's it. We extracted all of fields from our structures, and we are ready to start the genetic algorithm. According to steps of the algorithm, we have the initialization step here, and then we will enter the evolution loop. So let's start with the initialization phase of the algorithm, initialization step, and we're going to create an initial population of randomly generated solutions for our problem. So let's create an initial population. So we are in the initialization step of our algorithm. Let's create an initial population here. But before that, we need a template for our individuals. And to do this, I'm going to define an empty individual as a template, which has some fields, some properties. One of them, and the most important, is the position in the search space. That can be referred to as chromosome as well. But I'm going to use position because it is a common phrase among all evolutionary algorithms and all metaheuristics. For example, if you've seen our tutorial on particle swarm optimization, or if you've seen our source codes published on yarpus.com on other algorithms, then you've seen that we used position and this field name to refer to the value, to the exact position of represented solution in the search space. So we use this phrase to make the codes compatible. Okay, we have position, and that's empty for now. This is just a template here. Also, I'm going to define empty individuals, cost value, or the objective value. You can use any name you want. I'm going to use the cost. And that's empty too, and I think that will be enough. So let's add another section here, and this is the template for empty individuals. We have a template for empty individuals, and in initialization phase we must copy this template to create an array of individuals, empty individuals, and then we will fill in the blanks. Which blanks? Here. The position value and the cost function for every individual defined in initial population. So let's create pop as repeated version of the empty individual. We will repeat the empty individual using repmat. Repmat repeats everything in MATLAB. It is a repeat matrix. The original meaning is repeating matrix, and it can repeat anything, including structures. So we are going to repeat empty individual. But what number of empty individuals are needed? We must repeat to reach n pop members. So we are repeating to get n pop members as n pop rows and one column. We are going to create an array of structures that has this shape, n pop by 1. And finally we get n pop members, which are gathered together as a column vector. So we have an array here and we initialize this array. And next we must fill in the blanks. So we start a for loop for I equal to 1 up to n pop for all members of this initial population. We're going to create random positions and then we are going to evaluate them to find the related cost value. So first of all, pop I, the ith member of the population, dot position, the position of the ith member of population, can be generated randomly and that will work fine. By initialization, we mean generating random solutions for our problem. To generate solutions, we can use randi, and randi will accept a range of integers, for example from 0 to 1, and a size. For example, if we want to create a matrix with 5 rows and 6 columns, then it will generate a random matrix and the members of this matrix, the elements of this matrix are either 0 or 1. And this is a range actually. If you put instead of 110, then you will get a matrix with integer elements and the value of elements will be 0 up to 10 inclusive. And here from 0 to 1 there are just 2 integers, 0 and 1, and we can generate any matrix with these random numbers. For example, if you hit the up arrow here, you reach the command history, and if you run the same command again, you will get another matrix, and again, and you see that the output changes every time I call randi function. That's a random generator. So I can use randi function to create a point in search space. And what's the search space we have? We refer to problem, which contains 10 binary variables here. So we must call randi returns integer numbers from 0 to 1. That's 0 or 1. And we return one row of problem.envar elements. And that's it. We have 10 zeros and ones randomly generated, and if we call this command again and again, we will have different solutions, and these are starting points of our genetic algorithm. So let's create random solutions using this, and one row and envar columns. That's it. And we created a new solution, a random solution here, and we're going to evaluate this. So popi.cost will be equal to cost function evaluated at this position. So we're going to pass the position of popi to this, and that's it. We evaluated the solutions here, and we have initialized the population successfully. For now, let's output the pop, and let's add a field named pop here and set it equal to this pop, and this will return the out value here. If we run this script, this incomplete script, we will get this. I'm going to run this by hitting F5 function t5, and I have out here, which contains population, which is an array of 20 by 1 structures. And if I get out.pop, I have this here, and if I get, for example, outpop1, I get this. This is the first solution in population, and the cost function is 6. So we have 6 ones here. Let's count 1, 2, 3, 4, 5, and 6. It's correct. The second population member is this, and if we want to compare these two individuals, then which one of them is better? Obviously, the first member of population is better, and this third one has just only one in the position, so I think it can be the best member of population. And for example, if you want, you can have the cost of all population members here, and if you hit enter, you'll get answers, and to gather them inside the matrix, you can use the concatenator operators here, and you'll get this, the cost value for all members, all individuals in the population. So we have 2 members here, the third member of population and the 15th member of population. They have both one in their positions, and the worst solution I think is 8 here and 8 here. And if we want to sort these individuals, we can sort them according to cost value, and we will reach there soon, and we will implement functions which sort a given population. So for now, we've implemented the initialization phase of our genetic algorithm, and we will implement the other steps of the algorithm as well. Before we start to implement the main loop of the algorithm, let's add a new parameter, a new variable here, which contains the best solution ever found. And we denote it by best sol, and this will contain the best solution ever found for this problem. For example, after initialization, we must have the lowest value of cost function, and we must store the corresponding individual in best sol. But before we start initialization, best sol.cost should be the worst value possible for a cost function, so it must be infinity. Because if we're going to compare this best sol to another individual, in the first comparison, best sol should be the loser of the competition. So we must set the cost value for best sol equal to infinity, and then after we evaluated pop I here, we can check if pop I.cost value is less than best sol.cost, then it means pop I is better than best sol, and if in the beginning of the initialization phase for I equal to 1, if we are performing this comparison, then because cost value for best sol is infinity, then this condition will be true, always true. And if this condition holds, and if it is satisfied, then best sol must be equal to pop I, and that's it. At the end of this for loop, we have best sol, which contains the best member of population, and that's the definition of best solution ever found. And in the rest of algorithm, in the rest of process, we will get track of best solution ever found, and we will update best sol regularly. And let's store best sol inside out variable, and we have best sol here, and I'm going to save this and run the algorithm, and let's check for the out. It contains a single structure here named best sol, and out.best sol will be this, and for the latest run we had this individual as the best solution ever found in the GA. And that's it. We created a variable to get the records of best solution ever found. Okay, let's add a title to this part of the code. This is the results part. And let's add another array that keeps the record of best cost at the end of each iteration. So let's add the best cost of iterations. And we have maxed iterations, for example, 100 iterations. And to store the best cost at the end of any iteration, we must have 100 empty slots. And to do so, we need to have an empty matrix. And we need to initialize a matrix. So let's create the best cost matrix here. And we can use initializers like zeros and others. I'm going to use nan here because it creates a matrix which its members is nan, not a number. And it's a good idea to use not a number for not measured values. And we're going to create a matrix with max it rows and one column, and that's it. We created a matrix which can contain max it numbers as best cost at the end of any iteration. So here we're ready to enter the main loop of the algorithm. To do so, let's the main evolution loop, and that's a for loop for iterations equal to 1 up to max it. And this will run for max it iterations. And this will repeat the crossover, mutation, and selection and sort steps again and again for max it times. And then it will exit the loop and it will return the result. And just remember to add the best cost here as the field of our output variable 2. And here we're ready to implement crossover and implement the mutation part, and then merge, sort, and select the new population of the next generation. To perform crossover, we need a population which consists of some empty individuals. And what's the number of individuals? We can set the number of individuals or offsprings created in the process of crossover equal to the size of population, npop. Or we can define the number of offsprings with a parameter with a ratio according to the npop. For example, let's define the npc as the percentage of children, for example, or crossover as a parameter, params.pc, and normally this is set to be 1, and that's the number of children, number of offsprings created in the process of crossover is equal to the number of individuals in the main population. So the default value for this parameter is 1, but you can decrease or increase this by having this parameter and generate more or less individuals in each generation of the algorithm. And let's add the PC parameter to our app1 too. And we have PC, the percentage of crossover or percentage of children equal to 1 for now, and params.pc. And let's compute the number of offsprings here by nc, which is defined as pc times npop. But we're going to round this to have an integer, so we can use the round function to round this number to the nearest integer, or we can use floor or sale as we wish, and round is fine for this step, I think. And for some reasons we need this to be an even number, and that's why, because we have the crossover as a two input, two output operator, and we return two offsprings from each crossover operation. So the number of offsprings should be an even number. So we must have this as an even number. To do this and to convert NC to an even number and to ensure that's an even number, we divide this by 2 and then multiply the rounded number, the integer number, by 2. So this is an integer number and it's a multiple of 2. So 2 times any integer will be definitely an even number. And that's to ensure that we have even number of children in our offsprings population. So now we have NC offsprings here. And let's create the initial population here. I'm going to create PopC, the population of children here. And I'm going to use this line, a line similar to this, to repeat the empty individual for NC times. Okay, let's rip math empty individual for NC by 1 times, and that's it. We created an initial population to hold the values of offsprings. However, for the same reason, we set NC to be an even number, and that's because we have 2 offsprings at the end of each crossover operation. It's better to organize our population of children in a matrix with 2 columns. So we have 2 columns here, and let's divide the number of rows by 2. So this is a matrix with NC elements totally, and it has NC divided by 2 rows for NC divided by 2 crossover operations. So we organize our PopC in a 2-column matrix to make easier to deal with the crossover and individuals created by crossover. Okay, this is the initialize offsprings population, and let's perform crossover. For crossovers from 1 up to NC divided by 2, that's the number of crossovers will be performed. And we're going to create 2 individuals, 2 offsprings, at every iteration of this for loop. And first of all, we need to select some random parents, and that's easy to implement. In the next step, we will implement other methods of selection here. But for now, the random selection will be enough. Okay, let's select parents. And to do this, we must pick 2 random numbers, 2 random indices from this population. And we know that the number of individuals in this population is npop. So we need 2 integer numbers randomly generated in the range of 1 to npop. And remember, they must be different. And to ensure that we have 2 different values for 2 parents, one way is that we shuffle the indices from 1 up to npop, and actually it's equivalent to creating a permutation of indices, and then pick up the first and second element in the permutation. Let's see how we can do this. Randper will create random permutation of, for example, 8 elements, and that's it. You see, this is a sequence which contains all of numbers in the range 1 up to 8, and it has a random order, and that's known as permutation. And we created a randperm of length 8, and we pick 2 and 4 as our parents. And as another example, we can call randperm again, and this time 8 and 4. And if we call this time we have 2 and 3. And that's it. Let's create a random permutation let's name this as Q, for example, and let's create a random permutation of n pop parents. And first parent is the member of population, which is indicated by the first element of this random permutation. And this is the first parent, and the second parent is the member of population, which is indicated by second member of this random permutation. So we've selected our parents randomly, and now we're ready to perform crossover. To perform crossover, we have some options here. We talked about the single point crossover, double point crossover, and uniform crossover in the binary domain. Remember that? And we're going to implement these crossover operations as well. So for the first operator, we're going to implement the single point crossover. Let's define a function which returns two outputs, y1 and y2, and let's name it single point crossover. And this will get x1 and x2 as two parents, and this will return y1 and y2 as two offsprings. So this is the general structure of our crossover operations. Here we have x1 and x2, which are the positions of our parents in the search space, and we will return y1 and y2 as the positions of our offsprings in search space. And to perform single point crossover, we need to randomly pick a cutting point, and this number can be after first element, after second element, after third element, and after seventh element of this array. And you cannot cut from end. That does not make sense. And so the cutting point will be an integer number from 1 up to 7. And in this case, it's 7. In general case, it's 1 less than the number of variables in the chromosome. So we must pick a number randomly in the range 1 up to n-var minus 1. So what's the n-var? The number of variables in the sequence. It can be determined by counting the number of elements in these sequences, x1 or x2, okay? N-var equals to number of elements in x1. And let's pick a cutting point. I'm going to pick this using j rand I. This is a random number, integer random number from 1 up to n-var minus 1, and that's it. That's a integer random number, and its value will be 1, 2, 3 up to n-var minus 1. And now we're ready to perform single point crossover. Okay, y1 will be consisted of two parts, one part from x1 and one part from x2. x1 part will be from 1 up to jth index, which is determined randomly, and the other part will be x2 j plus 1 up to end of array. And that's it. That will create our first offspring. So we have this, and we can define y2 in a similar way. y2 will have its first part from x2 and its second part from x1, and we've defined y1 and y2, and it will work fine. You can check for this by calling this function. It's the single point crossover. Let's save this, and I'm going to use this, and after that, after we run genetic algorithm, we will implement other crossover operators as well. Okay, for now, we're going to use single point crossover. Okay, we have single point crossover here, and we must apply this to the positions of these two parents, and then we will have the positions of our children, which are contained in pop-C. And which one of them? The pop-C in the case row and first column will be our first offspring, and the element in the second column of the same row will be the second offspring created by a single run of crossover operation. Okay, let's define the position of this population member, this offspring, and let's define the position of the second offspring as, let's continue this line here. This is y1 and this is y2. Remember that we returned the position of our solutions here, and we accept the positions of parents as well. So we are going to return the position of first child and the second child, and this will be the output of single point crossover, which gets the position of first parent and the position of second parent, and that's it. We pass this as x1 and this as x2, and we will get y1 and y2. And this is the crossover part. We are going to perform crossover here, and then we have defined our offsprings and we have determined the position of our offsprings in the search space. Here we can evaluate the newly created solutions, popck1 and popck2, two offsprings which are born right now, right here. And if we evaluate the cost value for these, then we are increasing the number of function evaluations, and that means we have a high computational cost here. But that will help us to check for that if mutation, which is carried out after this, was helpful or not. If mutation is able to make the solution better or not. And in this case, we have several options. We can evaluate the children here, or we do not evaluate here and we evaluate the solutions, the offsprings, after they have mutated. And we're going to do that here. But if you wish, you can use this scenario. Copy all of offsprings into a new population and then apply mutation on those copy versions, and then merge the original population, the unmutated offsprings, and the mutated offsprings. And to do so, we must have a higher value of function evaluations, and it can be acceptable for some problems and it cannot be acceptable for other problems. It's up to you to select which scenario you're going to follow. But here I'm going to apply the mutation on these offsprings. So here we have a population of offsprings which are not evaluated, and I'm going to mutate these offsprings in the next step. Okay, we have a mutation step here. Also, we can apply mutation with a probability. For example, with a probability of 10%, we can mutate our offsprings. It can be modeled with a parameter. It can be handled with defining a new parameter named as probability of mutation. Here, we're ready to perform mutation on our newly created offsprings.